In this video, we're going to talk about the importance of physiological buffers. They're really important for dealing with excess acid or base in the human body. Specifically, we're going to talk about the buffers that are necessary to buffer blood pH and the fluid in cells, in all cells. So the first buffer we're going to talk about is the carbonate buffer. So in the carbonate buffer, H2CO3, or carbonic acid, it acts as a weak acid. And NaHCO3 is a salt, right? The sodium ion kind of gives it away that it's going to be a salt. And it's a salt of the conjugate base, right? Where the conjugate base is HCO3 minus, and this conjugate base is provided by the salt. So that conjugate base, remember, comes from the salt breaking up into Na plus and HCO3 minus. So again, that's the conjugate base itself. H2CO3 is the weak acid. And now the carbonate buffer is really important in our blood. We can suffer from something called acidosis if there's too much acid, or alkalosis if there's too much base. So for example, if blood pH is greater than 7.45, that's called alkalosis. And alkalosis is really about having too much base. And this can be very dangerous. So how does the carbonate buffer deal with this? Well, basically the weak acid, the carbonic acid, would react with the extra base, right? We said it was too much base, so too much hydroxide. And what it would do is it would give away its H plus to the OH, and it would leave behind HCO3 minus, so one less hydrogen, and give away that hydrogen of the weak acid to neutralize some of the hydroxide and make water. So basically, it's giving away one of its protons to neutralize the OH to make water. What if there's too much acid? pH, blood pH less than 7.35 is called acidosis. It can be caused by a number of causes, but really that's all about too much acid. So how does the carbonate buffer help deal with this? Well, here's where the conjugate base comes in. The NaHCO3 supplies lots of HCO3 minus. It can react with excess acid, or H3O plus, extra hydronium ions, and really take on one of those extra hydrogens. So you'll have H2CO3 and water, kind of reforming the carbonic acid. So it's a weak acid. There's lots of the intact carbonic acid in solution. So that's how it deals with too much acid, too much H3O plus. It takes its conjugate base, HCO3 minus, reacts it with the H3O plus, reforms H2CO3, carbonic acid, and water. You've got too much OH. The weak acid H2CO3 can give an H plus to that OH minus to make water, and HCO3 minus. So it's a really cool conjugate acid, conjugate base pair. Let's just write those out for carbonate just to be sure that we know the conjugate acid, conjugate base pair here for the blood carbonate buffer, H2CO3 and HCO3 minus. So that's a super important physiological buffer. The next one we're going to talk about is the phosphate buffer. And so this is NaH2PO4 plus Na2HPO4. Now, with these two, it's really important that we keep track of which chemical we're talking about, and always check labels carefully and check problems carefully for what we're talking about. But NaH2PO4, well, each of these is known by a couple of names, but NaH2PO4, I would say, is probably most often modernly referred to as sodium dihydrogen phosphate. So there's a sodium, two hydrogens, and a phosphate. That's probably my preference to call it sodium dihydrogen phosphate, NaH2PO4. Now, its partner in the phosphate buffer, Na2HPO4, I feel like is maybe known by more names. Some people say disodium phosphate. Maybe sodium hydrogen phosphate is probably my preference because you're calling out the hydrogen and then the phosphate. You do have to know that there's two sodiums in that case. You have to know that HPO4 is a 2- charge and there are two positive sodiums. But anyway, Na2HPO4 is the second chemical we have listed here. And so I usually call that sodium hydrogen phosphate. So again, let's try this. Let's try sodium dihydrogen phosphate. You just really have to double check what you've got and what you're supposed to have. And let's do sodium hydrogen phosphate. I feel like that's typically the accepted names of the polyatomic ions, with sodium coming first. So this buffer is really important. This buffer really regulates pH in internal fluid of cells. So it's really critical that they maintain pretty consistent pH. And so in this case, the sodium dihydrogen phosphate, has an extra proton to donate. So that one's acting as the acid. And the sodium hydrogen phosphate, Na2HPO4, has one less hydrogen, so that is acting as the conjugate base. So the conjugate acid itself is H2PO4 minus, and then the conjugate base would be HPO4, 2 minus charge. So how does this deal with excess acid or base? Well, let's first react the acid, H2PO4 minus. How does it deal with an excess of base? What if there's too much base, too much OH or hydroxide? The OH can react with H2PO4 minus. The H will go to the OH to neutralize it, and it will just leave behind a single HPO4 2 minus. And then H will get together with OH to make water, and it'll be able to neutralize an excess of base. What about excess acid? Well, excess acid is going to react with the conjugate base, HPO4 2 minus, plus an excess of acid, H3O plus. So that acid is going to react to form, the HPO4, the conjugate base, is going to pick up an extra H plus proton to make H2PO4 minus. And when hydronium gives up an H plus, it will just leave behind water. So it is able to deal with too much acid or too much base, a little bit of excess acid, a little bit of excess base, and the phosphate buffer can deal with it. Just like the carbonate buffer in the blood can help keep pH steady, the phosphate buffer can regulate pH in the fluid of cells. Now, buffers have their limits. They can get buffer systems can get basically overloaded. But in general, they really help keep pH consistent in biological systems.